With EEG, electrical activity from the brain can be recorded using several electrodes placed on the scalp. These electrodes pick up changes in voltage from the neurons firing throughout the brain, and this data can be analyzed to extract patterns which correspond to different neural processes. So using this technology, researchers have been able to identify a specific waveform, the P300, as a neural indicator of decision. With a neural marker for choice, a system can be designed where options are presented while monitoring brain activity for the P300, and thus the P300 Speller was created, a system which presents letters to be selected using brain data, ultimately allowing users to spell out entire messages. This invention holds immense potential for improving the lives of patients living with physical communication barriers by allowing them to speak using only their thoughts. So this is Chatterp. And we are McGill NeuroTech.
Hi, my name is Sebastian. I'm on the front-end team.
I'm Lucas.
My name is Chris.
I'm Sarah.
My name is Nikan and I'm the lead for the front-end team.
I'm Kelly and I lead the research team.
My name is Danielle.
My name is Navisha and I'm on the research team.
Hi, I'm Lean. I'm part of the hardware team.
My name is Emily Snook.
I'm Janisha and I'm part of backend.
My name is Gabriel.
My name is Jess.
I'm Marley. I'm lead for the backend team. The innovation of the project comes from the fact that we're looking at things at a higher level, and the fact that we're trying to use contextual and semantic awareness to improve the speed of typing for users.
Using an open BCI, we endeavored to create, from scratch, an accessible and enhanced P300 paradigm. Building the system required a collaborative effort from our research, hardware, front-end, and back-end teams. We wanted our final result to provide an affordable, efficient communication aid for individuals with physical communication barriers. But first, we had to get it to work.
One of the main challenges we had with OpenBCI was first off the hardware setup. Like getting the data in the first place was incredibly difficult. There's nothing that we could use to have like a benchmark to say, this is our data in comparison to known good data that was generated using the exact same hardware. Touching the battery pack / touching your laptop at any point in time will increase the noise by magnitudes.
But we've been having a lot of issues with our electrodes and getting the proper signals. I'm pretty familiar with how to sweep hair out of the way and get a nice spot on the scalp just to put the electrode right in there. A little gel and some nice conductance, and then that usually seems to do the trick.
But it didn't. Luckily, we were able to reduce noise in our raw signal by using a second-order bandpass Butterworth filter. The frequency components forming the P300 wave fall between a range of 0.5 and 20 Hz, and so we eliminated any oscillations outside of this. Pre-processing our data helped to overcome the challenge of acquiring decent signal.
You need to tell what happened.
VCAT.
We were able to produce a sufficient accuracy using our classifier. We stuck with linear discriminant analysis, and basically we fed filtered data in epochs of 600 nanoseconds in windows surrounding the target and non-target stimuli. And we took the maximum probability from that LDA classifier for each row and column and took out of each row which one had the max response, and out of each column had the max response, and then recorded that as our prediction for the speller's letter.
So we enhance efficiency of the system and improve user accessibility with two modes, Predictive Text and Emoji. To get a better idea of how these two modes work, here's a look at the front-end division of the team.
So in today's day and age, text just doesn't have the same kind of tone that you can have with emoji. It just allows people to express their emotions in a much more efficient way. So several features that we built into the product relied on our work with the research team. For example, the Predictive Text model, which basically allows the app to predict the word that you're going to say based on the letters you've already typed, which just eases the user's use of the product and makes typing a lot quicker, as well as the text-to-speech API. I guess the hardest part was the integrating with backend, because we're talking about two teams that speak in two different languages and that don't know the other team's language. So for backend it was Python, and for frontend it was JavaScript. To overcome it, we brought the backend and the frontend teams together and kind of discussed in the most basic words how we would theoretically integrate it, and then went online and Googled to see what kind of methods we could use that allows us to integrate these two languages.
So me and Marley were talking. Instead of sending in real-time timestamps for each flash and interval, we're just going to send in time intervals between the flashes are going to be.
The site uses a WebSocket to establish real-time bidirectional communication between the front and back ends. This is implemented via the use of the JavaScript library Socket.io, which is available as a Node.js module, and a compatible Python library on the back end. With both the front and back end emitting and listening on the same port, the front end is able to send a start message to the back end with a delayed start time, which allows for synchronous initiation of the grid flashing animation and live data processing from the EEG. As soon as a P300 signal is reliably correlated with a row and column, the backend emits a message event through the socket with an array containing the row and column as integers. The front end is perpetually listening for any message event on the port, and whenever one is received, it reads the value of the contained element and appends it to the text being communicated.
In the end, we did get a couple trials where we had a very good P300 response. All of that would pass through the classifier and through our entire pipeline and end up spelling the word that the person was looking at. Our team is relatively small, and we'd all been relatively new to the entire BCI field. I was the only person who had touched Python before. It was an incredible learning experience. I think we were really happy to actually visualize our data on our own and create this entire pipeline, because if you think about it, this is not just software, it's not just analysis, and it's not just BCI work with the hardware. It's combining everything, getting it in real time, and creating a speller into it, which requires its own logic and its own branch on the side. The type of skills you need to create a screen that flashes letters versus to graph and to have the EEG data show up on your screen, and compare that to the skills you need to manipulate and to analyze data, those are all completely different. We were really happy to also get it working at some points, and getting working data, and then finally being able to see that peak with the P300 was really satisfying.
In the end, we were able to assemble and train a team of mostly beginners, and we made something that works. We want to continue working on this project, and in the future we'll be trying to add much more in terms of predictive analytics in order to infer conversation context and to better predict following words and maybe even entire basic phrases. We're thankful to NeuroTechX and to OpenBCI for their continual efforts to strengthen the NeuroTech community. It really supports groups like us to create and explore the applications of interfacing technology with the brain. Thanks for watching!